Hey everyone, in this video we're going to talk about section 5.3, which is about solving exponential and logarithmic equations. So finally, after a couple of sections of talking about different properties of logarithms, we're going to now start applying them for their intended purpose, which was solving equations. Okay, so now we actually have inverse operations to go between exponential or logarithmic forms. First things first, though, since we've talked about some of those properties, I think it's worthwhile to just go over some of the basic properties of logarithms, so that way when we recognize some different forms, we know how we're going to simplify those, and those should be automatic. So I'm going to have you go ahead and pause the video. I want you to try to fill out this table of how these different forms of logarithms, whether the log with base b, the common log with base 10, or the natural log with base e, think about how those different forms would simplify. So pause the video. When you're ready, unpause and we'll go over it. All right, welcome back. Okay, here's where we should have. So the whole first, you should notice that each of those rows are exactly the same. So those properties are the same regardless of what the base of the logarithm is. So like for instance, in that first row, if we have a log with a base b and then the argument also has a b, well, we know that in this case that exponent can come out in front. So we'd have y times log base b of b. And then from that third row, we know if the base of the logarithm and the argument is the same, that's equal to 1. So all of these are going to be equal to y. They're all equal to that exponent. Okay, we know that log base b or log base 10 or log base e, no matter what, if the argument is 1, it's 0. And the reason being we know is because any base raised to a 0 exponent is equal to 1. Okay, we talked about that third row, and then that fourth row we saw, if we have that exponential with the base b and the logarithm also has that base b, well, since those bases match, I know that's just going to be equal to my argument. So all of those should be equal to x. So keeping in mind some of those properties is really important, so that way when they come up when solving equations, we know how to simplify. Okay, so we're going to look at a couple different examples here of solving various different equations. And the thing that you should know is that there's oftentimes a lot of different ways that you can go about doing this, okay? So I'm going to show you one way. We might talk in class a little bit about maybe some other alternate options are, or if you think of through something and you're like, hey, would this work? Definitely ask in class, make a note, and we can go over it, okay? I do have a couple of just like common starting places of maybe where you would want to start. So first, isolating any sort of logarithmic or exponential part of the equation, that's really important. So that way we're just looking at the exponential and we're not looking at any of those other transformations or constants that can be, added or multiplied to it. We should condense or expand the logarithm as needed. So if you're given something that has a lot of different logs, log of x plus log of y minus log of z, for instance, it's helpful to get that into a single logarithm with a single argument, okay? Third, okay, rewrite the expression as a logarithm or exponent, okay? So if you can, converting between exponential and logarithmic form is helpful. And then fourth, if you have an exponential equation, something else you can do without having to go into a logarithm is to try to rewrite both sides of the equation using the same base. Okay, so we're going to see all of these different methods in these examples. So the first one we're going to look at is example 1. So it says we're going to solve 64 times 1 over 4 raised to the negative x divided by 5 power, and it's equal to 4. All right. Okay, so first thing that I see here, this is an exponential equation. I'm always going to try to go ahead and isolate that exponential base. So our base is 1/4. So I'm going to divide both sides by 64. Okay, so that's going to leave me with 1 over 4 raised to the negative x over 5 power. Okay, and then I have 4 over 64. I'm going to go ahead and simplify that. So let's see. So 4 over 64 is equal to 1 over 16. So it's equal to 1 over 16. Okay, in the current form that we have now, I'm going to go ahead, we're going to try to use that fourth step that we have. So it says that we're going to try to rewrite both sides of the equation using the same base. So I see here that we have a 1/4 and we have a 1 over 16. Okay, I can easily manipulate that 1 over 16 to be 1 over 4 squared, or using an exponent property, I know that's also 1 over 4 quantity squared. okay? So doing so, I'm going to have 1 over 4 raised to the negative x over 5 power, and that's equal to 1 over 4 squared. So now that we have it in this form, really what I'm trying to do is I'm trying to figure out, well, what's going to make those exponents be the same? I already have the bases that are the same, so what kind of value of x do I need to have so my exponents match? Because really, remember, the goal of solving an equation is to make the left side and the right side be equal to each other. Okay, so in this case, since my bases match, I'm only focused on how to make those exponents match. So I'm going to set the exponents equal to each other. And that's a pretty easy equation to solve. I'm going to go ahead and multiply both sides by 5. And we'll get x is equal to, or negative x is equal to 10, which means that x is equal to negative 10. Okay, there's one way that we can solve this. There's a couple other different ways to solve it. If you want to know those ways, definitely ask and we can go over it in class. All right, example 2. So this is going to give us a logarithm equation. So we're going to solve log base 4 of 7 minus 2x, and that's equal to 2. All right, so for this method that we're going to use, I think I'm going to go ahead and we're going to try to rewrite this as a logarithm or exponent. So for instance, okay, we have a logarithm. It's going to be easier to solve this maybe if we convert it into its exponential form, okay? I'll write that down. Okay, so what do we know about that? Well, I know that the base of my exponential is 4, okay? I know that the exponent is 2, so I'm going to have 4 squared is equal to, and then the argument is what that exponential is equal to. So it's equal to 7 minus 2x. Now, I see that this is going to be a really easy equation to solve. We just need to use a little bit of algebra. So I'm going to have 16 is equal to 7 minus 2x. Subtract over our 7. It's going to be 9 is equal to negative 2x. Divide by negative 2. I get x is equal to negative 9 over 2, or that's equal to negative 4.5. All right, okay, so we solved our equation. Before we move on to example 3, and you might be itching to do that, one thing just to note is that logarithm equations, we do need to check for extraneous solutions. And let's think about why. Okay, where have we checked for extraneous solutions before? Well, we've checked those when we solved like trig equations, okay? And we also did that when we solved rational equations. And so what we're looking for is, do our solutions, when plugged in, give us some sort of value that's going to be undefined, okay? And why would logarithms have undefined behavior? Well, we know that the argument of a logarithm must be a positive number, right? It can't be 0, can't be negative. Okay, so we need to make sure that when we plug this value back in to our argument, I don't get 0 or I don't get a negative number. Okay, so it's really important that we go back and we check that. So let's go ahead and do that. So checking for extraneous. Okay, so I'm going to have log base 4 of 7 minus 2 times negative 4.5. And it's equal to 2. Sorry, my fridge is refilling its ice. Okay, one common misconception that people often have, that I've seen students have, is that, oh, we got a negative number for x, so that must be extraneous. No, remember that the extraneous is going to come from like what happens when we plug it in. So don't just discount it because it's negative. We want to just make sure that it actually gives us a number that we want. Okay, so log base 4 of, okay, so negative 2 times negative 4.5 is going to be positive 9. Okay, I see that we're already kind of in the clear, but I'm going to keep going. So 7 plus 9 is 16. And I see that log base 4 of 16, well, that would be 4 to the what power equals 16. That's going to be 2, so 2 is equal to 2. So that is a true statement, okay? The other way that we could do this, and we can double check this, we'll talk a little bit more about this when we talk about what the graph of this logarithm is, but since we know that logarithms must have positive whole numbers inside their arguments, I can just check to see what the domain of this would be. So I'm going to just set it to be greater than 0. I know it can't be 0, it can't be less than 0. So solving this, I'm going to get 7 is greater than 2x. So 7 halves must be greater than x. So x must be less than 3.5. And I see that our value is within that domain. Negative 4.5 is less than negative 3.5. So another way to check. All right, when you're ready, let's go ahead and turn over our page. So example 3 gives us an exponential equation. So we're solving 24e to the 0.067x is equal to 214. All right, so again, before we go ahead and try to do anything to it, we need to make sure that this exponential portion is isolated. So I'm going to divide both sides by 24. Okay, so that'll leave with e to the 0.067x. Okay, and then 214 divided by 24, I don't think is a whole number. I believe it's 107 over 12. All right, okay. So there's two different ways that we can go about solving this. I'll talk a little bit about both ways, but one way is to convert this into its logarithmic form. Okay, so if we did that, I know that the base of my logarithm would be e. Okay, so I'm talking about the natural log in that case. Okay, what it's equal to is 107 over 12. Okay, and then my exponent is 0.067x. Okay, we'll keep solving it and then I'll talk about our other way. All right, so solving for x, that looks pretty easy peasy. We're just going to go ahead and we are going to divide by 0.067. And then x is by itself. So in its exact form, it would be the natural log of 107 over 12 over 0.067. Or if we converted it into its decimal form, its decimal approximation, I should say, that's 32.656. Okay. You might be thinking to yourself, okay, do we need to check for extraneous solutions? Well, let's think about what kind of function we have. Well, we were originally dealing with an exponential function. And is there anything that are there any restrictions of what we can have in an exponential function? Hopefully you're saying no, and I would agree with that. The answer is no, okay? Because remember, the domain of an exponential function is negative infinity to infinity. We don't have any sort of restrictions on x, so my solution is my solution. Okay, the other way that we could have gone about solving this was to take the logarithm of both sides, okay? So basically, what that means is that I can take a log on both sides, and it doesn't really matter. I could use log base 10, I could use log base 4, I can use any sort of base logarithm that I want. However, since our base is e, I usually try to, take the logarithm with the same base as whatever the base of the exponential is. So because our base is e, I'm going to use the natural log, okay? So what this is going to look like is I'm going to have the natural log of e to the 0.067x. Okay, so I took the natural log of this side, and I'm also going to take the natural log of my other side. Okay, so you are allowed to take a logarithm of both sides, okay, because we did it to both sides of the equation. From here, now I can use some properties of logs. So here I see that I have the natural log of e. Well, since I have an exponent, I know I can bring that out in front. So that would be 0.067x times the natural log of e equal to the natural log of 107 over 12. Okay, and then what do we know about the natural log of e? Well, that we know that that's equal to 1. So in this case, this is what we're left with. That's the exact same as the equation that we did when we converted into its logarithmic form. So what this means to say is there's really two different solutions as to solving, whether to take the logarithm of both sides or to convert it into its log form. We end up getting the same thing, okay? We also would have gotten the same thing if we had done a logarithm that wasn't a base of e. We would have just had some extra log stuff because this wouldn't have been 1, but we still would have gotten the same answer. Okay, example 4, we'll keep this going on. Okay, we're solving natural log of x minus 4 plus 6 is equal to 11. All right, so again, since I'm starting with a logarithm, we probably are going to want to convert this into its exponential form. Sorry, I just got a text. Let's see. What was I saying? Okay, we want to convert into its exponential form. Can't do that, though, until the logarithm is isolated. So I'm going to try to get the natural log portion by itself, so I need to get rid of the 6 and the 2. So I'm going to subtract that 6 on both sides. will give me 5. I'm going to divide by 2. I'm going to get the natural log of x minus 4 is equal to 2.5. Or 5/2, whatever you want to leave it as. Okay, in this case now, let's go ahead and let's, again, 2 different ways that we can do this. Let's talk about the first one. Let's convert it into its exponential form. So the base of this logarithm is e, so I'm going to have e. It is equal to 2.5, and then the argument is x minus 4. Okay, so that just means I need to add 4 over to both sides, so x is equal to 4 plus e to the 2.5 power. Or its decimal approximation is 16.182. Okay, let's talk about that other way that we could have done this. So we got to here. Okay, other way that we can do this is we can say, just like how in the one that we did before, we took a logarithm of both sides, something else we can do is we can do what we call exponentiating both sides. Okay, so what that means is that I am going to make both sides of this equation an exponent of some sort of exponential. Again, because we're dealing with the natural log whose base is e, I am probably going to exponentiate with a base of e. Okay, so what I can see here is now, okay, that equation that we originally started with, well, now that's become exponents onto exponentials. And what's nice about this now is I know here, I know that e to the natural log, well, those undo each other, so we are left with just x minus 4, and then I have e to the 2.5 power. I have the same thing that I did when I used when I converted it into its exponential form. Okay, so again, we get to the same place, just that operation is a little bit different between those. Okay, before we move on to example 5, though, this was starting with a logarithm. I do need to make sure that I don't have an extraneous solution. I do see, though, when I plug in 16.182 minus 4 is a positive number, so we're going to be good to go there. So, not extraneous. All right, last one, example 5. We're going to save example 6 to do in class, but example 5 will be our last one. We're solving log of x plus log of 3x plus 1 is equal to 1. So this equation has 2 logarithms. What we want to do is we want to use log properties to combine this into a single logarithm, okay? So I see that that logarithm has addition in between it, so I know that I'm going to take those. And they both have the same base, so they're both base 10. So I'm going to take their arguments and I'm going to multiply them. So I'm going to rewrite this as log base 10 of x times 3x plus 1. Okay, now that I have this as a single logarithm, what we want to do is, we want to try to convert this into its exponential form. So this logarithm's base is 10, like I said. So its exponential form will be 10. It's equal to 1, so that's my power. 10 to the first power is equal to x times 3x plus 1. Okay, so solving this from here, so we'll have 10 is equal to, I'm going to go ahead and distribute this through. So I'll have 3x squared plus x. Okay, and then we are running into a quadratic. So I'm going to go ahead and subtract 10 on both sides and set this equal to 0. So I have 3x squared plus x minus 10 is equal to 0. So now we're going to use our different methods for whatever we want to use to solve the quadratic. So again, let's see if it factors. Let's see. Let's make this be a plus 3, and then nope, that's not going to multiply to 10. What am I doing? Plus 2, minus 5. Wow, hopefully you got there faster than I did. Okay, here we go. So our solutions are going to be x equals 5/3 and x equals -2. Okay, before we circle it and call it a day, we do need to check to see if those are extraneous. So the important thing about this example when checking for extraneous solutions is we want to plug it back into the original unadulterated one, the not adulterated, the unmodified one. There we go. Because if I try to plug it in here, that is going to kind of change what we have. So I always just think, let's just plug it back into the first one. So plugging it in, that 5/3, okay, that is a positive number. I can plug it in there. Okay, and if I put 5/3 in here, 5/3 times 3 is 5, 5 plus 1 is 6, that's positive as well. We're good to go there. Okay, if I plug in -2, we're going to have a negative inside the argument of a logarithm. That's going to be undefined. Okay, so that -2 is not going to work. Same thing here. If I try to plug it in, that -2, I'm going to have -6 plus 1, that's -5. I also have an undefined portion in that logarithm. So -2 is going to be an extraneous solution. So we have one solution, one extraneous solution. All right, okay. That's all we're going to do in this video. The next example that we have is going to kind of use a couple different properties and a new kind of method that we maybe haven't used before or seen before. So it's better to do it in person. Anyways, I hope you all enjoyed this video, and I will